This is part 2 of a series on weights initialization. In this video, we will look at a weights initialization method proposed by Xavier Glorot and Yoshua Bengio. This video was produced in Korean and translated into English. My voice is AI-generated text-to-speech. In the last video, we went over the basics needed to understand the weights initialization. In this video, we will look at Xavier Glorot's method. We will look at how to initialize the weights so that the input signal and gradients can flow smoothly through each layer during the forward and backward propagation. This allows us to obtain the optimal variance of the normal distribution for weights initialization. And in the same way as above, we find the optimal range of uniform distribution for the initial weights. Finally, we will apply Keras Glorot Initializer to a network. In 2010, Xavier Glorot and Yoshua Bengio proposed an efficient way to initialize the weights of a neural network in this paper. They proposed a new initialization scheme that brings substantially faster convergence of neural networks. Now let's go through the method proposed by Xavier Glorot and Yoshua Bengio step by step. First, let's consider forward propagation in a neural network. During forward propagation, we would like the variance of the activations to remain constant across layers. Let's find the optimal variance of the initial weight distribution in the forward direction. Let's consider a subnetwork consisting of a lower layer and an upper layer as shown below. There are Ni neurons in the lower layer and Ni plus 1 neurons in the upper layer. I is the layer number. The output of the lower layer is Zi, and the output of the upper layer is Zi plus 1. Zi plus 1 can be written like this. Here, f is the activation function of the upper layer. The weight matrix between the lower and the upper layer is Wi. We would like to set the initial values of Wi efficiently. When we try to initialize Wi using a normal distribution with mean 0 and variance sigma squared, we will try to find the optimal sigma squared. Assume that the means of both Z and W are 0. Our goal is to make the variance of the lower layer output equal to the variance of the upper layer output. This allows input signals with similar distributions to flow from lower layers to upper layers. Let's find the variance of W that achieves this goal. Let's first find the variance of Zi plus 1. Since Zi plus 1 is f of Si plus 1, var of Zi plus 1 can be written as follows. If the activation function f is sigmoid or hyperbolic tangent, we can assume that f is a linear function near the origin. And this can be expressed like this, using the formula we generated in the previous video. Using the formula for the variance of the product of two independent variables, this can be written as follows. By the assumption, both the mean of W and the mean of Z are 0. Therefore, var of Zi plus 1 can be written like this. Here, since the objective is to make this term and this term equal, we can cancel the two terms in this equation. Then the variance of Wi becomes 1 over Ni. This is the optimal variance of weights obtained from forward propagation, satisfying the objective. Let me give you an example. If the number of neurons in the lower layer is 100, the initial weights of the upper layer are set by drawing them from a normal distribution with a mean of 0 and a variance of 0.01. I referred to the documents below. Next, let's consider backward propagation in a neural network. During backpropagation, we would like the variance of the gradients of loss with respect to the output S to remain constant across layers. Let's find the optimal variance of the initial weight distribution in the backward direction. Let's consider a subnetwork consisting of a lower layer and an upper layer, just like the previous page. There are N neurons in the lower layer and K neurons in the upper layer. In the lower layer, this output is Si, and in the upper layer, this output is Si plus 1. The activation function of the lower layer is F1, and the activation function of the upper layer is F2. The weight matrix between the lower and the upper layer is Wi. We would like to set the initial values of Wi efficiently. When we try to initialize Wi using a normal distribution with mean 0 and variance sigma squared, we will try to find the optimal sigma squared. We assume that the means of both S and W is 0. Our goal is to make the variance of the gradients of the loss L with respect to Si plus 1 propagating from the upper layer equal to the variance of the gradients of the loss L with respect to Si propagated to the lower layer. This allows backward signals with similar distributions to flow from upper layers to lower layers. Let's find the variance of W that achieves this objective. The gradients backpropagated from the upper layer are combined here. The gradient propagated through this path is multiplied by Wi and passed to the lower neuron. And then F1 prime of Si is multiplied. The sum of all these is the gradient of L with respect to Si. Again, our objective is to make the variances of these two gradients equal. This can also be obtained using the chain rule. Si plus 1 is the dot product of F1 of Si and Wi plus Bi. And the partial derivative of the loss L with respect to Si can be written as follows by the chain rule. This term is the partial derivative of the above equation with respect to F1 of Si, so it becomes Wi. And this term is F1 prime of Si. So this equation holds true. Since f is assumed to be a linear function near the origin, f prime is assumed to be 1. We take the variance on both sides of this equation. And the right-hand side can be expressed like this using the formula we generated in the previous video. Using the formula for the variance of the product of two independent variables, this can be written as follows. By the assumption the mean of W is 0, and this can also be assumed to be 0. Then we can obtain this equation. Since the goal is to make this term and this term equal, We can cancel the two terms in this equation. Then the variance of Wi becomes 1 over Ni plus 1. This is the variance of W that can achieve this goal during backward direction. We found two optimal variances for W. One is for forward propagation, and the other is for backward propagation. If the number of neurons in the lower and upper layers are equal, the two variances are equal. Otherwise, the two variances are different. We cannot say which one is better to use, so we use an average of the two. Then the final optimal variance of W becomes as follows. This is the weights initialization method proposed by Xavier Glorot and Yoshua Bengio. Let me give you an example. If the number of neurons in the lower and upper layer is 100 each, the initial weights of the upper layer are set by drawing them from a normal distribution with a mean of 0 and a variance of 0.01. Next, let's look at how to initialize the weights using a uniform distribution. Now that we know the optimal variance for a normal distribution, we can also find the range for a uniform distribution. There is a uniform distribution with a range from -a to +a. The average of this is 0. For this to be a probability distribution, this area must be 1. Then the height will be 1 over 2a. The probability density function of this distribution can be written as follows. The variance of this distribution will be 1/3 a squared. And as we saw earlier, the following two conditions must be met. We already know the variance that satisfies the above conditions, and the variance of a uniform distribution must also be equal to that variance. Therefore, a satisfying the above conditions is as follows. That is, the weights are initialized using this distribution. Let's see how to use Xavier Glorot's weights initialization formula with a simple example. Given a neural network model like the one below, set appropriate initial distributions of W1 and W2. There are 50 neurons in the input layer. There are 80 neurons in the first hidden layer and 100 neurons in the second hidden layer. If we use a normal distribution, the initial distribution of W2 is as follows. 80 is the number of neurons in the lower layer, and 100 is the number of neurons in the upper layer. The initial distribution of W1 will be like this. The variance of the initial distribution of W1 is slightly larger. This is because the number of neurons in the lower layer is smaller. If we use a uniform distribution, the initial distribution of W2 will be like this. The initial distribution of W1 is as follows. In this case, the initial distribution of W1 is slightly wider. In Xavier Glorot's method, when the activation function is sigmoid or hyperbolic tangent, it is assumed to be linear near the origin. However, this assumption does not hold when using activation functions such as ReLU. In the next video, we will look at Keiming-He's method for initializing weights using the ReLU activation function. Finally, let's apply Xavier Glorot's method to a neural network using Keras. Import Keras initializers. Let's create a neural network model like this and apply Xavier Glorot Initializer to both hidden layers. Create Glorot Initializers for normal and uniform distributions. The number of neurons in the input layer and the two hidden layers are 50, 80, and 100 respectively. Generate input data X using a standard normal distribution with mean 0 and variance 1. Build a neural network model. Create an input layer and add two hidden layers. The weights of each hidden layer are initialized to Glorot normal, and the activation functions are set to hyperbolic tangent. Create an output layer. Create a model that checks the outputs of the first hidden layer, S1, and create another model that checks the outputs of the second hidden layer, S2. Create a model for training. We will only check the initial weights and the outputs of the hidden layers, so no training is performed. Check the initial weights of the hidden layers, W1 and W2. And check the outputs S1 and S2 of each hidden layer when input data X is fed into these models. Let's check the standard deviation of W1 calculated by Keras when using a normal distribution. Then, use this formula to manually calculate and compare the results. Let's check the range of W1 calculated by Keras when using a uniform distribution. We check the range with the minimum and maximum values of W1. Then we will use this formula to manually calculate and compare the results. And we will also check the standard deviation of the normal distribution and the range of the uniform distribution for W2. Let's check the results. When using a normal distribution, the standard deviation of W1 calculated by Keras is 0.125, and the standard deviation calculated by the formula is 0.124. The two results are similar. The two results are the same for W2. When using the uniform distribution, the W1 initialized by Keras are in this range. The results calculated by the formula are as follows. The two results are similar. For W2, the two results are similar. Let's run this code. The results are as follows. So far, we have looked at Xavier Glorot's weights initialization method. In the next video, we will look at Keiming He's weights initialization method.